Hello everyone, I hope that you are fine. Welcome to another session of Robotics Lab. In this lab we shall try to implement A-star algorithm in Matlab. So this algorithm has already been developed by someone and also the code is available in Matlab. So we don't need to write the code again because it's pretty lengthy, and to save time and to avoid reinventing the wheel, so we just download this code and try to understand how it works and how we can use it to find the shortest path. So what you have to do, you just have to visit this website of mathworks.com, and here you have to log in, and then you shall find this one, A-star search for optimal path tutorial. So just you have to click the download button here, and then it will be downloaded as a zip file, and then you can extract it in any folder. I have already downloaded it, and as you can see it's available here, and you have to open this one, A*1.m, and the others are, this is a tutorial, this is like some information if you want to learn more about A-star algorithm, and there are some functions, for example distance, expand array, insert open, and others. So yeah, so let's open this one. This is the main file, A*1.m, and here you can see that this is an interactive A-star search demonstration, and it is copyrighted by MathWorks. And one important thing is that you have to see the author of this code, and I think this is clearly available here in the license maybe. Okay, the author was available in the, this is Paul Prem Kumar. This is the author of this code. Okay, so here you can see that we define a 2D map array. Okay, this is a 2D algorithm. It can also be converted to 3D algorithm, but for simplicity we only now consider a two-dimensional array. So this array, we define here what will be the maximum size of our array or the map. So this will be 10 by 10 along x and y axis, and then we have this array stores the coordinates of the map and the objects in each coordinate. So then we define the map. As you remember from the previous labs, we have this, we know how to make a map, and in this map we store 2. So 2 means that in the map 2 represents a free space, and then we initialize some variables. We define the maximum x and y coordinates. So here it says that for obstacle, if in the map we have to show the map obstacle, it means we have to write -1. The target will be represented by 0, and the robot will be represented by 1. It means start location will be 1, and the free space will be represented by 2. This is because the computer, it understands only the digital, or you can say numbers. Okay, discrete values. Okay, then we have to begin the interactive obstacle target start location selection. So in couple of here you can see that this code will get some inputs from the user. It says that okay, if you want to select the target, then you have to press the left mouse button, and similarly you can select number of obstacles, and also you can select the target, the start location. So yeah, so here till this code, this algorithm will get input from the user about the location of the target, the location of the obstacles, and the location of the start point. You can see here, this will be the location of your initial or the start position. And then what we do, we initialize the value given by the user, x and y, to the start, and we put this in the map. In this command we represent 1 in the map, which shows the start location, and then we plot it. We plot to visually show the results. And then we have some list we have to define for A-star algorithm. If you remember, we have to define open list and closed list. In open list there were nodes that were not yet visited or discovered, and then we have in a closed list, and in a closed list we have nodes that have been already visited, or you can say already have been discovered. So after that we have, what the first step is, we put all the obstacles on the closed list, okay, because we cannot visit them, so we put them in a closed list. So for there we have 2 for loops here, one for x and one for y axis, and step by step we put all the obstacles in the closed list. Set the starting node as a first node. So we start from our first node defined by the user, which is a beginning point, and then after a couple of steps the algorithm actually starts here, and there's a while loop here, and this while loop will keep executing till your target is reached, a target node is reached or found, you can say. So the first thing, it will call a function which is expand array. This function will be called with some parameters: x node, y node, path cost, x target, y target, closed max. So it will get the start location, the target location, and the closed list, and then it called this function which is located here. This is expand array. So in this function, what it does, it has a function to return expand array. This function takes a node and returns the expanded list of successors with the calculated f and value. So if you remember from the A-star algorithm lecture, that what we do in how we do that, we try to calculate for each node, we try to calculate the f value. The f cost was the sum of g cost plus h cost. So if you remember the for example, this is the start point, and let's say this is our current node, and here we have the target point. So what was the G cost when we are at a current node? So the G cost was the distance between your current node to the distance between your current node and the start node. Oh, it's not drawing accurately. Then let me select the into shape. That might help. Okay, the result is same. So okay, so yeah, so this was the G cost, the distance between your start and the current node, and the H cost was the distance between your target node and the current node. And the sum of these two distances, we call it our F cost. So here in this function expand array, what it does, it tries to first find the successor or the neighboring nodes, or you can say the adjacent nodes to the current node, and also it calculates the F cost of each of the adjacent node. Okay, so here you can see in this, here exactly the calculation is being done here. So yes, here in this line number 29. So we are adding this our G cost. This is the G cost and this is the H cost. So we are calculating the F cost here. So in this line expand array exp count 3. So what we are doing is we are calculating the G cost, which is the cost of traveling to the node. And then in the next step, in the next command, we are calculating the H cost, in which we calculate the distance between the target and your current node. So once you have the G cost and the H cost, you just have to add both of them to get your F cost. So once this function is finished, the result will be stored in this array, which is exp array, and so this process will be repeated a couple of times. So we have to, so the algorithm, it keeps looking for the adjacent node and select which, and calculate their F cost and select the node which has the minimum F cost. If you want more details, I think you should consult the lecture. So here you can see find out the node with the smallest fn. So as you are familiar with these best first search algorithms, they're different from breadth first search. So dijkstra's algorithm and the A-star algorithm, they both are best first search algorithm because they select the best node from your adjacent nodes. Okay. Set X node and Y nodes to the node with minimum Fn. Okay, let's see what's here in this function. Insert open. Function to populate the open list. So yeah, this function makes an open list every time to explore new nodes. And then we have minimum function. This function takes the list open as its input and returns the index of the node that has the least cost. So yeah, so it within the neighboring or the adjacent nodes, this function tried to find the minimum cost node. Okay, in the next step we have update the cost of reaching the parent node. If you remember that if we find a node that has a shortest or the less cost as a previous cost, so what we do, we update its parent. We say okay, the parent is the new node which has the least cost or the comparatively less cost as compared to the previous one. And yeah, once the node has been visited, we say okay, move this node to the closed node. And if there is no path to the goal, let's say if the goal lies within the obstacle or the obstacle covers all the possible path, then I think it's not possible to find shortest path toward the goal or a feasible path even. So in this case, the algorithm will return that it will say no path exists to the target, and this variable value will be 0. Once the algorithm has run, the optimal path is generated by starting off at the last node if it is the target node, and then identifying its parent node until it reaches the start node. This is the optimal path. So yeah, so so this is the same thing we learned in the lecture, that it always search the backward the tree. Starting from the goal node, it start looking backward. So I think in the next step there will be this backward search will be executed. So if X value is equal to target and Y value is equal to Y target. So here, yes, if the target is reached, so what it does, it start looking for traverse the open and determine the parent node. So for each node, it tries to look for its parent, and here in this while loop, it's also getting the grandparent. So parents and their parents and their parents and their parents till it reaches the start node. And once it reaches the start node, this will be the shortest path from start to the goal. And then we can plot this path like from this command. You have this optimal path variable, which we find here in this while loop, and in this list or array we have stored points consisting of x and y axis, which represent the path or the coordinates of the node leading to the goal. And then we just have to plot it, and after that we yes, there we also make some to look the visualization more appealing and presentable. We add some more plots. We also plot the start and the target location, and if there is no path, then we also display this message that sorry, no path exists to the target. So let's quickly run this algorithm and see its results. So here it says that okay, first you have to select the target. Please select the target using the left mouse button. So let's say our target is located here. So this is our target location, and it says select obstacles using the left mouse button. To select the last obstacle, use the right button. Okay. So first, is it clear that this is our environment, or you can say a configuration space, and it is clear that it has 10 nodes on the x-axis and 10 nodes on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually it's 11 units, 11 meters away, but the nodes are 10. Similarly, in this direction also we have 10 nodes, and we have discretized it using grid cells. We have this each block, it represents one cell, and this grid can be converted into a graph, and then we can use A-star algorithm on this graph. But we need to first define how our environment looks like, the map of the environment. So we say that okay, this cell which has a coordinate of, on the x-axis it's 3, and on the y-axis it's 9. So we say okay, our target is located at 3 and 9, and then we have to tell where the obstacles are located. So we say that okay, here we have obstacles. Let's make all obstacles here. And let's try to make it a little bit tough, so it's not that easy to find path. Like you know these games, for example, when you play a game, computer games or games on your smartphone, and there are some puzzle games where you have to find some path. These games, they also use, in the background, they also use some path search algorithms. Almost all types of games, they use these path search algorithms, and most commonly used algorithm is the A-star algorithm, because I think I have already defined this in the lecture, the reasons for why we use A-star algorithm, and you can consult lecture, but this is the most commonly used algorithm in the games, in the robotics. Okay, so the last obstacle, it says that you have to select the last obstacle with the right click, and then next step is please select the vehicle initial position using the left mouse. Okay, let's say we have the initial position here. You see that the algorithm started from here and it's searching for the shortest path, and this is the shortest path to the goal we have. I think here one step is missing. It should start from here, but it started from here. I think it's the problem with the plotting, but this will be your shortest path from your start to your target position. So is it clear now? I hope that whenever you play games, for example a war game where you have to find your enemy, any types of games, for example, if you have seen that this game, for example these shooting games where there are teams of players, and then the one player is selected by you, which is controlled by you by your keyboard or mouse, and you are controlling it, and then there are some players that are being controlled by computer, and they always find you, they always try to locate you where you are. So how they locate you? The computer using path search algorithm, for example A-star algorithm, to find you. For example, if you are located here and the initial location of this automatic computer player was here, and it wanted to search, it wanted to know that how to reach to your location, and then we have here the walls of the room or the boundaries. So it uses this A-star algorithm to follow you where you are located, and once it reaches you, it will maybe attack you or fire on you. So yeah, so this algorithm, it has a lot of applications, a lot of useful applications, starting from games to robotics to artificial intelligence, and even the routing. For example, when you use this your internet, for example, so your internet they also use some kind of routing algorithm or search algorithms to send data from one router to another location, so that your data can travel the most efficient and shortest path. Okay, so yeah, I hope that this is clear. You can practice it, you can try to make more difficult for it to find. Yeah, so now it's time to give you a task here. It was easier to implement. So the first thing you have to do is you have to make a map like this. Okay, I'm making it roughly, but you have to do it, you have to organize it by yourself, how you want to implement it. So here is your start point, and then here you have obstacles here. Okay, let me make the obstacle with some other color. And here is your target location. So what you have to do, you have to find the shortest path between the start and the target location. And what else you need to do is the first task is find the shortest path in above map. Using A star algorithm. And using dijkstra algorithm. All this. Okay, so this you have to do. You have to make a map like this, and similarly you have this user interface. You just have to click the mouse to place your start and the target location, and then you have to click mouse button to place the obstacles, and then you have to use your A star algorithm, which is already there, to find the shortest path. And once you finish it, just make a screenshot and send me the picture by email. The second thing is you have to find the path using dijkstra's algorithm. For that you have to know that how you can convert this A star algorithm into dijkstra's algorithm. So you have to look in the code, and you have to find out that how you can convert this A star algorithm into dijkstra's algorithm. And once you convert it into into dijkstra's algorithm, it's very simple. It's just one step. Okay, if you have listened to the lectures and the previous labs, you should know that how to do that. So it's just one step. You have to do that. Once you convert it into your this dijkstra's algorithm, you have to find this path again and take a screenshot and just send it to me by email. And yeah, we shall finish this lab here, and thank you for listening to me. And if you have any questions, you can always contact me by email. I shall try to answer.